On Earth, we have a simple intuition about travel. Hours by car, a couple of hours by plane, days at most to cross an ocean. In space, that intuition no longer works. There are no straight routes or fixed highways. There are moving orbits, planets that are never in the same place, and a clock that rules over any engine. When we ask how long it takes to reach another planet, we usually imagine a fixed distance, a point A and a point B. But in the solar system, A and B are constantly orbiting around the Sun. Each journey is a choreography, and the travel time depends less on the distance in kilometers and more on how we dance with those orbits. To leave Earth, you first have to escape its gravity. That already requires an enormous speed, on the order of 11 kilometers per second. But that's just the first step. Once outside, the spacecraft doesn't travel in a straight line toward the destination. It falls around the Sun in a new orbit. The key is to design that orbit so that it intersects at the right moment with the orbit of the target planet. This is called an orbital transfer. The most classic one is the Hohmann transfer. In essence, it's like changing lanes on a circular highway. You increase or decrease your speed to move from one orbit to another without making any sharp maneuvers. You don't aim at the place where the planet is now, but at the place where it will be in months or years. Furthermore, it's not enough just to arrive. If you only cross paths with the planet at full speed, you fly by it and keep going. To enter orbit around that world, you have to slow down. And slowing down in space means using fuel. A lot of energy to go up, a lot of energy to come down. That's why travel time isn't just about going as fast as possible, but about finding a balance between speed, available fuel, and what you want to do once you arrive. Fly by, orbit, or land. With this in mind, let's look at the nearby neighbors, Mercury and Venus. They are the first steps toward the Sun. On a map, they seem easy, but physics tells a different story. Mercury is the closest planet to the Sun, and that detail complicates everything. When you fall toward the Sun, your spacecraft accelerates enormously. The solar gravity pulls you as if you were going downhill on a gigantic mountain. When you reach the Mercury region, you're moving extremely fast. And if you want to stay in orbit around that planet, you have to lose much of that speed. It's like going down a mountain pass at full speed and expecting to stop just before a sharp curve. That's why the probes that went to Mercury didn't take the shortest route. They took the smart route. Instead of falling directly, they used a series of flybys to adjust their speed. The spacecraft passes close to Earth, Venus, and Mercury itself several times, using the gravity of each body as a brake or a little push, depending on what's needed. Each flyby slightly alters the trajectory and speed, until the spacecraft can finally enter orbit without needing an impossibly large engine. The result is that, even though Mercury is relatively close in terms of distance, missions take years to arrive and stay there. The extra time is the price we pay for not carrying a gigantic rocket solely to slow down. Venus, on the other hand, seems like a more hospitable destination. Its orbit lies between Earth's and Mercury's, and the minimum distances between the two planets are shorter than the ones separating us from many other worlds. In fact, in terms of energy required, Venus is one of the cheapest destinations in the solar system. Several missions have taken only a few months to reach it since launch. From the trajectory perspective, it might seem like an almost simple journey. A relatively short Hohmann transfer, a trajectory correction midway, and orbital insertion. But again, the difference between arriving and staying appears. To orbit Venus, you also have to slow down, and spacecraft usually combine engine braking with the use of Venus' own atmosphere to decelerate. In some cases, aerobraking is used. The spacecraft partially dips into the upper layers of the atmosphere repeatedly, using the resistance of the gas as a natural brake. This allows fuel savings at the cost of a longer and more complex entry phase, measured in months. The journey doesn't end when the spacecraft reaches the planet. It ends when the final orbit is stable enough to do science. If we only look at the time numbers, we might say that reaching Venus takes a few months, and a mission to Mercury can take between 6 and 7 years. But if we look at the physics behind it, we understand why one of the seemingly closest destinations became an extreme challenge, and why travel time is, in reality, the result of a negotiation with the laws of gravity. Even in this inner solar system neighborhood, there's already a clear pattern. Every time we ask for something more ambitious, the journey duration tends to grow. Mars is the planet we've dreamed of moving to the most. It has mountains, deserts, polar ice caps, and days that last almost the same as a day on Earth. But when we ask how long it takes to get there, the answer is never a fixed number. There is no standard journey to Mars. There are time ranges, fuel compromises, and a schedule imposed by celestial mechanics. The distance between Earth and Mars changes all the time. Sometimes they are relatively close, separated by just a few tens of millions of kilometers. Other times, the Sun is in the middle, and the distance multiplies several times. It doesn't make sense to talk about an average distance and expect a unique travel time. What matters is the geometry of the moment when we ignite the engines. When the orbits align well, a key opportunity arises, the so-called launch window. This window opens approximately every 26 months. If you launch at just the right time, you can use an efficient transfer trajectory and arrive with a reasonable energy expenditure. If you launch outside that window, you'll need more fuel, more time, or both. With current technology, a typical mission to Mars takes between 7 and 9 months to reach. This is not an arbitrary number. It's the result of balancing flight time and fuel. If you tried to go much faster, you would have to accelerate more when leaving Earth's orbit and then slow down more forcefully when arriving at Mars. That means bigger tanks, heavier rockets, and less mass available for payloads, scientific instruments, or habitats. If instead you wanted to save as much fuel as possible, you could accept longer, slower trajectories. But the price would be having a spacecraft traveling for over a year just to arrive. The missions we've already sent provide concrete examples. The rovers and orbiters that have reached Mars in recent decades fall within that 6 to 9 month travel range. Each mission takes advantage of a specific window, with a slightly different trajectory design, but always playing the same game, leaving Earth's orbit with the right speed, falling toward a solar orbit that crosses Mars's orbit, and meeting the planet at the right moment. During those months, the spacecraft doesn't travel in a straight line. It's constantly falling around the Sun, following a path calculated down to the last detail. For a robotic probe, 7 or 8 months in space is acceptable. A handful of teams on Earth monitor it, correct small course errors, and wait for the big arrival day. Time becomes an engineering variable. But when we think of human crews, those months in transit take on a different weight. In such a journey, the crew would be exposed for a long time to cosmic radiation and solar storms, with limited protection. They would live in microgravity, with bone and muscle mass loss, changes in the circulatory system, and psychological effects from confinement. Every extra day of travel increases the risk dose. That's why there's so much talk about faster propulsion technologies. Thermal and electric nuclear engines are being studied, which heat fuel or power ion engines with much greater efficiency than current chemical rockets. In theory, with these systems, we could reduce the trip to Mars to a few months, maybe half the typical time. The spacecraft would accelerate for much of the journey, instead of giving a single initial boost and then coasting along the orbit. But these engines present significant technical and political challenges: managing nuclear material, safety, added weight, and the need to test them first without humans aboard. However, even if we manage to reduce the flight time, the journey to Mars is not solved just by the outbound trip. We need to think about the entire mission. If you send a crew, you need a plan to return. That plan also depends on the launch windows. You can't just arrive, spend a few weeks, and depart whenever you want. You have to wait for the orbits of Earth and Mars to align favorably again. Some mission architectures propose short stays of just a few weeks with a quick return, but these require very energy-intensive and complex trajectories. Others accept longer stays of more than a year on the Martian surface, waiting for the optimal time to return. When we add everything up, the result is that a round-trip human mission to Mars could last anywhere from 2 to 3 years, a few months to leave Earth's orbit and reach Mars. A prolonged stay on the surface, using the journey to do science, test habitats, and learn to live on another world. And then, again, months of travel back. Time becomes the framework for the entire adventure. The spacecraft is both a means of transportation and a home. And every design decision, from the size of the tanks to the habitable volume, is conditioned by those months in transit. Meanwhile, robotic missions continue to pave the way. Today, Mars is populated by orbiters that measure its atmosphere and climate, and by rovers that move just a few meters per day. From our perspective, their movement is frustratingly slow. But on a planetary scale, their patience pays off. Every image, every rock analysis is only possible because a spacecraft spent months traveling and was then slowed down precisely to enter orbit or land with parachutes, rockets, and aerial cranes. The time spent getting there is rewarded with years of data sent back to Earth. Jupiter is the largest planet in the solar system. It is about 5 times farther from the Sun than Earth. This means that, even in a favorable alignment, the spacecraft has to travel hundreds of millions of additional kilometers. With chemical rockets, there are no magical shortcuts. Typical trajectories to Jupiter take about 5 or 6 years of travel. It's a huge leap when you've been thinking about the 7 or 8 months it takes to reach Mars. The first probes, like the Voyager missions, followed very special routes. They weren't just going to Jupiter. They used Jupiter as a springboard to the rest of the solar system. This technique is called gravity assist. The idea is simple, though the execution is complex. The spacecraft passes close to a planet and steals a tiny portion of its orbital momentum around the Sun. The planet doesn't even notice, but the spacecraft gains or loses speed depending on how it approaches. It's not a magic push. It's an energy exchange with a much more massive body. In practice, a mission to Jupiter usually combines efforts. First, the spacecraft escapes Earth's orbit with a big initial boost. Then it travels through inner space for months, sometimes using flybys of Venus or Earth itself to adjust its energy. Finally, it heads toward Jupiter's orbit, where it must arrive with the correct trajectory and speed to slow down and be captured by its gravity. Each flyby adds travel time but saves fuel. Again, the clock and the tanks are negotiating all the time. A clear example is a probe that wants to stay in orbit around Jupiter. If it arrives too fast, it would simply fly past. To slow down enough, it would have to fire its engines for long minutes or even hours, burning enormous amounts of fuel. Since this is unfeasible with chemical rockets, the route is designed so that the spacecraft arrives with a manageable speed for braking. The price is time. Years of gradual trajectories, gravity assists, and fine adjustments. Saturn is even farther away. It's about 9 or 10 times the Earth-Sun distance. Here, the typical travel time approaches 7 years with the technologies and trajectories we've used so far. The missions that have reached Saturn were not direct. They also relied on gravity assists and long detours through the inner solar system before targeting the ringed giant. The logic is the same. Stretch the journey to make it energetically possible. In the case of a Saturn orbiter, the challenge multiplies. It's not only about reaching the planet. You also need to slow down enough to avoid being ejected into deep space. This requires a large orbital insertion maneuver. During those critical minutes, the spacecraft fires its main engine as it passes behind the planet, out of sight from Earth. When it reappears, the orbit is either established or the mission has failed. It's a type of gamble that only makes sense if we accept years of previous travel to arrive under the right conditions. Between Jupiter and Saturn, there's also the problem of the environment. At those distances, radiation around the gas giants is intense, especially around Jupiter, whose magnetosphere is enormous. Probes must be shielded, and their electronic systems designed to withstand a constant bombardment of high-energy particles. This doesn't change the travel time, but it does affect the spacecraft's design and the amount of mass we can dedicate to protection, instruments, and fuel. The more demanding the environment, the heavier the spacecraft becomes, and the harder it is to accelerate and slow down. All of this is acceptable for robotic probes. They don't get dizzy, they don't get depressed, and they don't get sick. They can spend 5, 6, or 7 years crossing deep space before reaching the destination planet. Meanwhile, the teams on Earth continue with their lives, reviewing data from other projects, waiting for the arrival, and preparing observation plans. Time, on a human scale, dilutes. For the mission, those years are just an initial phase. For a human crew, the scenario would be very different. Thinking about a 5 or 6 year journey to reach Jupiter, plus the time required for any exploration and the return trip, leads us to missions lasting a decade or more. A spacecraft would have to become a self-sufficient habitat, with life support systems capable of functioning reliably for years. Problems like radiation, physical health, mental health, and equipment maintenance in an environment where any extra spare parts add mass and fuel consumption would need to be solved. Also, at those distances, communication with Earth is no longer instantaneous. A radio signal can take tens of minutes to travel. It no longer makes sense to talk about real-time control. Any manned mission would need to be extremely autonomous. It wouldn't be enough to have a control center sending detailed instructions. The crew would have to make critical decisions with limited information and delayed support. The travel time is not just a physical challenge, it is also an organizational and psychological one. It might be tempting to imagine exotic engines that drastically reduce these times. But with the physics we know today, even significantly improving propulsion, the order of magnitude would still be years for the gas giants. We can shave some time off by adopting more efficient engines, accelerating during more stretches of the journey, rather than just at the beginning. Still, turning a 6-year trip into a 6-month trip is beyond current engineering capabilities. The solar system is vast, and that scale cannot be compressed by mere will. Beyond Saturn, the distances become unintuitive. Uranus orbits nearly 20 times the distance between Earth and the Sun. Neptune, about 30 times. From here, those numbers are cold, abstract. But when you translate them into travel times with chemical rockets, they become almost a decade crossing deep space. And that's just to pass by, not to stop and stay. Uranus has only been visited once, and just in passing. A probe that left Earth in the 1970s took almost 9 years to get there. It didn't stay in orbit. It didn't slow down. It simply crossed the Uranian system, took images, measured magnetic fields and temperatures, and continued its path toward Neptune. The encounter lasted a few hours, maybe a few days if you add up all the useful approach time. 9 years of travel, a moment of front-row science, and then, once again, the void. If we wanted to do something more ambitious, like a mission that would enter orbit around Uranus, the problem grows. To slow down enough to be captured by the planet's gravity, the spacecraft would have to arrive with less relative speed or have a much more powerful engine and large fuel reserves. This implies even longer trajectories with additional gravity assists or heavy rockets dedicated almost entirely to the braking maneuver. In either case, the total travel time would still be on the order of many years. Neptune presents the same dilemma, amplified. The only visit it received was also a flyby. The probe took about 12 years from launch to reach the encounter with the farthest planet. 12 years for a single, unrepeatable pass in front of a world of which we know barely the basics. Its internal structure, the dynamics of its atmosphere, and the behavior of its moons. An orbiter that wanted to study Neptune for years would face an even tougher balance between time, fuel, and useful mass. For engineers, this translates to decades of planning and a mission that would likely exceed the working lifespan of many of the people who design it. At these distances, even light becomes slow on a human scale. A radio signal sent from Earth takes several hours to reach a spacecraft near Neptune, and just as long to return with a response or data packet. This means that any delicate operation, any maneuver, must be fully automated. You can't drive the spacecraft from the control room. You design the sequence, load it into the onboard computer, and wait. Hours later, you know whether everything went well or if something failed when it's already too late to fix it. Further out, in the region where icy objects like Pluto orbit, time stretches again. A flyby mission with a very energetic trajectory and a light spacecraft took almost 10 years to cover the distance between Earth and that small frozen world. 10 years during which the spacecraft made minimal corrections, sent data from interplanetary space, hibernated to save energy, and waited for the moment of the encounter. On the day of the flyby, the spacecraft crossed Pluto's system at such high speed that it only had a few hours to take the best images and measurements. Then it continued toward the Kuiper Belt, with no possibility of slowing down. If you wanted a spacecraft to stay in orbit around Pluto, you would have to accept a very different compromise. Either you launch a mission with a much more powerful rocket and large fuel reserves to brake, or you choose a less energetic trajectory that allows you to arrive with less relative speed at the cost of perhaps taking 15 or 20 years for the journey. Again, time becomes the currency of energy. You can spend more fuel to arrive sooner, or you can spend less by accepting decades of travel. In practice, this has made missions to the outer solar system almost always flybys. They're like trains that pass through a remote station just once. You take advantage of that pass to look at everything you can, with all instruments on, and then continue. The advantage is that you arrive in more reasonable times for a human project. 10 or 12 years from launch to the big scientific moment. The disadvantage is that you can't stay to observe how those worlds change over time, nor can you send a landing probe from a stable orbit. Now that we have a clearer understanding of how interplanetary times work, we must ask ourselves, if technology advances so quickly on Earth, why aren't we radically cutting those times in space? The answer starts with an uncomfortable equation, the rocket equation. Essentially, it says something simple. To go faster, you need to expel mass at high speed backward. That mass is the fuel. The more delta V you want, the more fuel you have to carry. And that fuel weighs. As it weighs more, you need even more fuel to accelerate that extra mass. It's a vicious cycle. The result is that with chemical rockets, Each additional meter per second of speed becomes more and more expensive in terms of mass. This explains why we don't launch giant spacecraft with massive engines to accelerate them for days. In practice, what we do is give a big initial push and then let the spacecraft fall under the sun's gravity, following a calculated orbit. That initial push has to be enough to escape Earth and place the spacecraft on a trajectory toward the target planet. But it can't be so large as to require an absurdly huge rocket. If we also want to slow down upon arrival, the problem doubles. All the fuel we use to brake also had to be accelerated at the beginning. It's like filling your car's tank with the gasoline you'll need to hit the brakes. That's why we use efficient transfer trajectories, like the Hohmann transfer. They're routes that aren't the fastest, but they're the cheapest in terms of energy. They allow us to reach Venus in a few months, Mars in less than a year, Jupiter in 5 or 6 years, and so on. Time is the price of using less fuel. For robotic probes, this trade-off is acceptable. For humans, it becomes more problematic, but physics doesn't accommodate our desires. There's another tool we make the most of: gravity assists. Instead of trying to accelerate the spacecraft only with its engine, we use the planets as slingshots. The spacecraft approaches, passes behind them in the right direction, and its trajectory curves and its speed changes. It gains or loses orbital energy depending on how the flyby was planned. This allows us to increase speed without using fuel, but it adds time. Each extra loop around the Sun, each visit to Venus or Earth for a boost, stretches the mission timeline. If we truly want to cut travel times, we need to change how we propel ourselves. And that's where future technology comes in, the one discussed in conferences and labs. One option is ion engines. Instead of burning large amounts of fuel in a few minutes, they expel ions at enormous speeds over months or years. The thrust is very small, almost imperceptible, but constant. Over time, this gentle acceleration can produce significant speed increases. They are ideal for probes that are in no rush and can afford slow but efficient navigation. They've already been used in missions within the inner solar system, and they could play a role in longer journeys. Another possibility is nuclear propulsion systems. An onboard reactor can heat a propellant and expel it at higher speeds than chemical combustion allows. This means more thrust per kilogram of fuel. In theory, a thermal nuclear engine could reduce the journey to Mars to just a few months. The concept doesn't violate any laws of physics. The challenge is engineering, safety, and politics. Launching reactors into space, ensuring they don't scatter in a failure, and testing complex technologies before putting people on board. Ideas like solar sails are also being explored. Large reflective surfaces that harness the pressure of sunlight to continuously push a spacecraft. The thrust is minimal but constant. For very light missions with little cargo, it may be enough to build surprising speeds over time. In the future, we could see fleets of small probes propelled this way, moving between planets. Or even sails pushed by lasers from Earth in more ambitious long-term projects. All these technologies promise to shorten travel times, but expectations need to be scaled. None of them will turn a trip to Neptune into a weekend outing. Going from 12 years to 8, or from 10 to 6, would already be a huge leap. The same for Mars. Reducing travel time from 9 months to 4 would be a revolution for manned missions. But with conventional physics, we're not going to achieve days-long trips to these destinations. The solar system isn't large because we haven't invented the right engine. It's large because the distances, orbital speeds, and energy limits put us in its real scale. Beyond physics, there's the human factor. Increasing speed significantly means almost always raising the level of risk. More energy at play, more demands on materials, more vulnerability to failure. Space agencies have to balance ambition with safety, especially when there are lives on the spacecraft. This caution also translates into longer times and more conservative trajectories. We don't just want to arrive faster. We want to arrive in a repeatable and reliable way. Still, when we look ahead, it's reasonable to think that travel times to the inner planets will be reduced. Mars, in particular, is the big candidate. The combination of more efficient engines, better radiation shielding, and more robust habitats could make a manned mission take less time than it takes today for a robotic probe. For the gas giants and the outer system, the horizon is further away. But each advancement increases the design freedom of missions.